Yeah, Viram, so take it away.
Okay, so basically, this discussion will be about sort of seeing why mathematical physics, in a sense, is a natural way to approach not only physics but maths, because most of the time when we're like researching either math or physics, the thing is like they complement each other. Sometimes while doing physics research, we come across a sort of a way to define things. And through those definitions, we construct new mathematical structures. And even the other way around too, like there'll be some mathematical structures which already exist, but we don't really know we can use it in this way. And somebody's like, okay, this kind of makes sense in this topic, and they use it, and it sort of works. So mathematical physics is all about this, I think. It's in its pure form, I would say it's a sort of abstract. It's a very abstract way to view nature, be it mathematical or physical. So we'll start off with a small example of what I mean, and we'll start off with something like everybody knows and likes, I guess. We'll start off with electrodynamics, if that's okay with everybody. Yeah.
Yeah,
Yeah,
that sounds good.
go for it.
Okay, good.
Yeah.
So I'll just write down the first thing that comes to mind in electrodynamics is obviously the Maxwell equations, right? The four equations. And obviously for this meeting, we'll keep it in vacuum. It's not really that much different when we consider currents and non-vacuum states, but just to keep the sort of meeting less
The main point.
calculate.
Yeah, to
Yeah.
drive it home. Yeah.
Yeah, sort of thing like that. We'll keep it in vacuum state.
Right.
So let me just write down the equations. I'll write this down in the most basic sort of sense, like
Yeah. Using just vector calculus. Yeah.
So
I think even Freeman Dyson has talked about this, where if the mathematicians had looked into Maxwell's equations earlier, so many differential geometry concepts that we have right now, like Lie derivatives and so on, would be found at least 50 to 100 years earlier. So yeah, it proves that there should be more communication between the fields.
Yeah, is it readable? I mean, it's sort of
yeah,
perfect.
Yeah, it's pretty legible. I guess if there are any questions, people will mention it in the comments.
Sure, yeah. This is E and this is B, obviously. This is, well, just so basically, just looking at these equations, we sort of see a resemblance, right, between B and E.
Yeah.
In a sense, like if we replace in the first equation, if we replace B with E, then we get the second equation. And in the third and fourth, if we replace B with E and sort of a negative sign here, we get this next two equations. In a sense, we can see that there's some sort of symmetry going on in these equations. So what I'd like to do, just as in the beginning of this discussion, would be to sort of discuss the sort of symmetries that we can directly see from these equations. And as of in symmetries, I mean the typical definition of symmetry is like how if sort of a coordinate is changed from dx nu to something multiplied to dx another coordinate, how that would sort of change the full equation. It basically coordinate change. That's the symmetry that I want to discuss and see. So yeah, like what do you guys think is just looking at this equation, what sort of, if I change E to, let's say, something multiplied with E, what sort of thing can I multiply it with to keep all the equations sort of in the same form? You
Mm,
guys, it's
uh,
your guys. Like you can sort
yeah,
of give
right,
any.
right. So I'm going to forget everything I know, and let's see if there is a new approach here. So, yeah, maybe if one thing we could possibly do is multiply the B equations with an electric field and an electric field equation, the electric field equations with a magnetic field, and see if we can generate some sort of symmetry there, if that would work.
So you mean we'll take another quantity which is like E cross B or something like that, or
Something, yeah, something like that, maybe,
okay,
if that can work. Yeah. What would
okay,
that do?
sure.
Yeah,
Well, we can always just write it down and try.
right,
So
right.
okay, so Rahul's idea is basically, well, let's say there's this new quantity A, which is we'll use cross products here, the typical definition of cross products, nothing fancy.
Right.
So this would just be E cross B. Well, B cross E, E cross B is just the sign change, so it's fine.
Sign change, right.
So if we take A, and okay, so the obvious next step would be to, let's say, take the divergence of this new A
Right,
and sort of see what we get.
right.
So this would be the divergence of E cross B.
Hmm.
So what would this be equal to basically?
So I guess it would you would have to use a Leibniz rule here. It would come into play with it.
Yeah,
Like,
and
yeah,
any sort of expansion, it would still be zero because
it would
the
be 0, right?
Right.
Okay,
right, even if
so
it's a Leibniz or any other
right.
expansion also.
Now,
So sure, so
what
we
would
get
yeah
yeah.
what would happen to the other two equations?
Okay, well, we have to sort of we have to find a way to get the other two equations from A.
From A,
So
right?
we have to define a new operator. So in which if we put A, we get these two equations as a sort of result. Well,
Correct.
I can't think of a direct sort of operator. Well, if you guys can, well, like you can always try it.
Let's see. So okay, so we need an operator that will so what we essentially need is for the two equations to be sort of sums,
As a,
or yeah, they each of them being 0,
sure.
or
Well, if
like, or rather they're multiplied to be 0. Yeah, there isn't really, I don't know, I can't think of a
yeah,
very
well, it's not
straightforward way.
a straightforward way. So
Right.
instead, well, if there's no straightforward way for this, we can always change the initial A consideration, and
Right.
we can say, well, we can say E plus B, right?
Okay. Yeah.
Okay, well,
Yeah. But
so just to keep it technically
yeah,
accurate, we'll say it's E, some sort of summation. It
some
doesn't
sort of
have to be
summation.
plus,
Right.
right? Some,
Yeah.
no multiplication.
Yeah.
So I'll just correct this then.
Yeah, because
So
yeah, in situations it won't really make sense to just add these two vector quantities.
right,
Yeah, that
exactly.
right.
So
Because of the dimensions, right?
exactly, that's the main problem. So instead of defining a direct sum, we'll define something like a sum.
Something like a sum.
Okay, and the one thing that you can always see from the next two equations are we see that the first one is a plus and the second one is a minus when we sort of replace the E and B. So if in a sort of way we can always consider a complex number, like a complex number case. So what I mean is A is E plus IB, for example. So
yeah.
I don't know, maybe you get
Like
this
there's
minus.
some sort of a conjugation happening there.
Exactly. So this is just the random consideration. We'll
Yeah.
see what happens. Like we can always see. So okay. And okay, so we'll do the same operations again. So if we take the divergence of this would again be 0.
Right.
Right. And now I think if we add the next two equations, so we get this curl of E plus B and plus dou by dou t of B minus E.
Mm.
Okay, so I'll just write it down here.
Yeah.
So we get plus okay. This is equal to 0, of course.
Hmm.
So again, we need some operator that acts on A, which gives this equation as a result.
Right.
Okay.
And it isn't really straightforward. So there's a multiplication by I somewhere and add it to the same thing or something of that sort happening, because you have a plane E plus B coming into picture. But again, yeah, no real straightforward way for that.
So instead of adding the last two equations, if we multiply the last equation with I and then add them, then we have like curl of E plus IB. But then
What happens to the partial
second
time? Yeah.
B minus IE. So that's like IA, I think. No, minus IA.
We were trying to get an operator that will act on A to get this result out
Right.
as an
Right.
output.
Right. Right.
Yeah. Again, I don't see any sort of direct operator that exists just like that. But yeah, well, so we might have to try some other sort of thing. Like we might have to choose E as some sort of non-trivial thing, something we can't just guess out
Right.
of
Right.
in
Right.
2 minutes or something.
Right.
So well, that's not a problem. Well, what we wanted to try to get from trying out these methods was a sort of approach to see how we can get these 4 field equations using a sort of an entity which has everything in it. So because A has info of E and B, and doing stuff on A, for example, will give you the first two equations here, which we nicely get. But the second two is not that obvious. Well, that's fine. The thing that we were trying is that we get the thing. So we saw in a sort of way we are look from the field equations, we are going up conceptually to a Lagrangian of whatever the theory is.
Right.
So obviously A is not in any form a Lagrangian, but in principle, that's what we were trying to do. Because, well, we obviously know that from the Lagrangian, by varying the different fields, we get these 4 equations.
Right.
Just
Right.
this form. So in principle, we were taking these 4 equations that we know, and we were sort of generalizing them up to something that they all have in common in a way, which was the Lagrangian. So, well, where exactly does mathematical physics sort of abstractness maybe come into this topic? So, well, I think that the abstractness of a theory will sort of present itself when we look at these functions, not as functions, as like, A plus B is equal to C, but as more as mappings. At least when we need a direct, maybe if we need some sort of oh, this could be on a sphere, or this could be on some manifold. If we consider the problem as maps rather than algebraic equations, we get a more pure form of the problem that we are asking, you can say. So instead of looking at the Lagrangian itself as as a sort of as an entity with these many terms, like some x plus y something something whatever, instead of looking at a Lagrangian like that, we can say that it is a functional that which has the position components and the time derivative of the position components. So that's where I'm trying to take this trial to. So I feel like the abstractness of the theory would be more eminent when we look at the mappings of
Right.
the concerned quantities.
Mhm.
If that makes sense. I don't know if I'm just saying some stuff, but does it make sense?
Yeah. I think I see what you're getting at. So like we've come across mappings and all of that mm, uh, when we consider sets and all of this, and we don't see how it is actually coming into the picture as of now. But what
Right.
you said about we are trying to find a certain unified quantity from which we get all these equations. And
Exactly.
yeah, that would as the viewers who are familiar with physics would know, would be from the action of the theory, which is basically the integral of the Lagrangian over the coordinates. And from that Lagrangian, that's what we're trying to do.
Exactly.
Yeah, essentially. So, but we'll still have to see, I guess, how the Lagrangian
Of
is
course.
essentially a functional. Yeah.
Right. So, I mean, the Lagrangian is a map basically, right? From the
Right.
it's not the phase space, right? It's the velocity space, I think.
It's a velocity. It's the velocity space. Phase space would
Real
be
number.
phase space would be the
Hamiltonian.
Legendre transform, which is the Hamiltonian approach. Right.
Exactly. So we can see the Lagrangian as a map from the velocity space to real numbers or complex numbers, whatever whatever theory we are talking about. So in a sense, it all goes back to mappings, basically. Mappings on different spaces to different spaces.
Right.
So, well, I mean, we could try to sort of come up with a basic Lagrangian properties of what a Lagrangian for this theory would. We can definitely try that instead of this sort of approach. So, just hold on. Yeah. Oh, it's not writing.
So I'm not able to see how the Lagrangian is a mapping from velocity space to, let's say, real number space.
Yeah, I'll show that.
Okay.
Yeah. I think Viram will go ahead with this, but to give you a glimpse of it. So what does the Lagrangian take? It's basically the difference of the kinetic and potential energies. And your kinetic term is usually dependent on some velocity components. And the potential term is usually dependent on some position. Or you can have effective potentials as well, which may be dependent on interactions, all of that. But we won't go into that. Very simple Lagrangian, where you have position. So your Lagrangian is a function that takes in velocities, which are the time derivative of positions, and spits out a number. That is.
Oh, I see.
Yeah.
Okay.
This is the definition of a functional. It goes from certain spaces, vector spaces, whatever, to and R. In the real yeah, the output is the real space.
Okay.
So yeah, that is basically it. And yeah, there is, yeah, I see this one approach where, yeah, definitely the Lagrangian thing is what we're trying to find, and mappings, and that's why abstraction helps. But one can even probably view the generalization through the generalization of the operators themselves somehow, because there is, yeah, there is some symmetry with how your dotting of the divergence acts and the crossing, which is essentially the curl,
Right.
acts. So maybe there is something there as well. I guess we will see. Yeah.
But in the thing you said, right, when we say symmetry, right?
Right.
So
Right.
itself is rooted in the Lagrangian.
That is true.
A theory is
Yeah.
always symmetric.
Right.
So, you know, if a theory has to be, that's symmetric only in the Lagrangian as it is in the field equations.
Right.
So
True.
as yeah, so I would, you know, it's sort of coming to the Lagrangian or Hamiltonian or some sort of quantity which contains all the relevant information about the theory.
Right.
And we do some operations on that and we get the field equations. So
Sure. Yeah.
okay, well, do you guys want to go ahead and maybe just try to get some info on the on how we can maybe construct the Lagrangian for this theory? Do you guys want to do that?
Yeah, why not? So without any prior knowledge, let's see. If I were to
Without
construct,
any prior knowledge.
right.
Okay, so yeah, well,
Yeah.
okay, so I'll start off very simple with just defining what a Lagrangian is. So without any mathematics. So it's like a Lagrangian is like it's a quantity. It's like a term, like let's say E itself. So, but the Lagrangian is another term which has different quantities. You know, it'll have position components, which is X, and the time derivative of the position. So, which is basically dou by dou t of X or X dot. So it
Right.
is some sort of expression which is a combination of these terms, X and X dot. Now we can sort of take the Lagrangian term and do operations on it. Operations could range from simple operations like you know, time derivatives or position derivatives or whatever. It could be that, or it could be something that we call variation, sorry, where we sort of it's basically like saying if the Lagrangian doesn't change if I change the coordinate like this. So yeah, if the technical term is variating the Lagrangian with respect to the field, well, that just basically means if I change the field or coordinate like this in some sort of way, the Lagrangian doesn't change. So that's what that's what a Lagrangian is, and its properties and so on. So, and we can always, so these four things that the four Maxwell equations that I've written, right? They can be considered as the field equations of a certain Lagrangian, the electromagnetic Lagrangian, let's say. So what field equations are is basically the equations that we get by variating the Lagrangian with respect to the coordinates. So yeah, here we get four field equations. We can get, depending on how we construct the Lagrangian and how many coordinates are there, we can get more.
Yeah.
Okay. So we will start by sort of constructing the Lagrangian. Now, in a very simple way, there's nothing really complex about this. And yeah, we'll just start with that. So Okay, so first let's say that the Lagrangian exists. Just to start. So like let's say that the Lagrangian is L. So this is the okay, well, we all know this. L is the Lagrangian. So what can we say about the Lagrangian by looking at these four field equations? Any ideas?
It's function of fields and their time derivatives.
Oh, exactly. So that's the first thing. So here, since we are talking about, sorry, yeah. Oh, sorry. So this we can say it's basically this. Basically, let's say x is the field or coordinate, and x dot. So we can say this is true because this is true for any Lagrangian. Okay, great. So we have gotten the first step at least. Okay, so now the next step would be to maybe write the E and B in terms of coordinates.
Yeah.
Because well, E is a field, B is also a field, and they would be, you can represent it in a sort of coordinate sense.
Right.
So I'm assuming you guys are familiar with the forms, differential forms, one forms, two forms, so on. Yeah.
Yeah.
Okay, great. So here,
we can maybe have a short crash course.
a short crash. Okay, sure. So okay, so let's say that we have some sort of vector field, any vector field actually, V. Okay, and let's say that we have a mapping F that takes V to R, where R is just the real numbers, real plane. Okay, so here this F would be the sort of is it called the covector form?
Yeah, it's a covector. Yeah.
Yeah, right. So this would be a covector of V. What that means is if I take a V input, put it in F, I'll get a real number.
Yeah.
Right. So that's all it means. And yeah, and differential forms is basically these things here. This is a differential form. We can call the elements of this in a sort of sense it's differential form. What I mean is if let's say V has the coordinates let's say xi. So does this make sense? Right? Yeah. So then we will have basically the what do you say, the sort of basis of F as dxi. Does that make sense? Sort of in a sense, so the basic thing about this entire thing is we can always have sorry, let's so if we say fi and element of V is xi, this would always be equal to 1. Or if we have I and j, it would be the Kronecker delta ij.
Right. It's sort of like defining an inner product or a dot product between these two things. One being a vector and the other being a covector, where it may be viewed even as a column and a row vector being multiplied together. It's all the same thing. Yeah, exactly. Yeah.
Exactly. Yeah. So the reason we choose to sort of deal with things in this covector form is because the results of covector form are real numbers. Right. And in real numbers, we can obviously do things like, we can multiply and divide regular, like, 2 into 2 is 4 type stuff.
Right.
So because we're dealing in R, we usually deal with covectors because they take the space and they give us R.
Right.
That makes sense?
Right. Makes sense.
Yeah. Okay. Yeah, sure. Okay. So without getting into too much detail, I can say that we'll define E as a one form. So a one form is basically a how do I say this? It's how do I say this actually?
It takes
One form.
yeah, it's because can we consider it to be like something like it takes in a vector position and gives a certain value of the field.
Right, exactly. That would yeah. So E we
Yeah.
can say is a sort of E itself is a sort of entity which will take a vector V and give a real number. Only one
Yeah.
vector is required for E
Right.
because it's a one
Right.
form.
Right.
So we will just write this as you know just the typical representations EI dxi. This is again expanded, depending on the number of dimensions and so on. E1,
Right.
E2,
Right.
so on.
Right.
And we will define B as a two form. So this would be, let's say, K dxi dj.
But now, why is
Like-
this a two form?
Oh, well, this is actually an interesting thing to think about because how do I say this? See, I can tell you in a sort of, I can't tell you in a simple way. One way that I can directly think of is looking at these equations, right?
Right.
When we in the mainly the next two, the last two equations,
Right.
when we sort of switch E to B. So
Right.
there is a sort of operation which from one form to two form, which is called the Hodge delta operation, I think. Hodge star,
Right.
sorry, Hodge star.
Hot star.
operation,
Right.
Which in which the Hodge double star would be -1 to the power something. It's
Yeah.
like minus some plus p square something.
Yeah.
So as if we define it as a two form
Yeah.
and we go ahead and sort of analyze it in this sort of sense, we can nicely define these two equations as a Hodge
Yeah.
as a difference in Hodge products.
Yeah. So there's actually there's actually, sorry to interrupt, but I think there is a baby version of this that we can go over. So if you noticed, when you deal with differential forms, there is the anti-symmetry relation. And you also see that with cross products. When the cross product is switched, a minus sign comes into play. And the way that the magnetic field is defined is velocity crossed sorry, that's the force. Never mind. So yeah, anyway, this is one thing that you will see, that there is some relation between the cross product and your differential form. And when you mentioned the hot star operator, right? In baby terms, it's actually giving you the complement space. So if if you have, let's say, your total space is 3-dimensional, you have something that's 1 dimension. The complement of that will be 2-dimensional, right? Which is orthogonal to what you have. So your hot star is essentially a generalization of this orthogonal complement relation into higher dimensions. And your cross product is with at least some sort of a derivative or whatever, is generalized into being this exterior derivative. But I guess we will see the exact way that connects in future videos. But yeah, that's just to give you some motivation, I guess, as to why it's a two form, B. Yeah.
So what if we choose electric field to be a two form and magnetic field to be a one form rather? Because it looks like if we change E and B, the equations look symmetric almost, right? So why not the other way around?
Okay, the thing is, we can actually choose it. The only thing that we have to sort of keep in mind is one of the should be a one, the other one should be a two form. And the two form will be defined as a magnetic field, and the one form will be defined as the electric field.
So it's
See, there's
more nomenclature, is what you're saying.
yeah, electric field, basically, yeah. So like, as long as we have an entity which is a one form and another one which is a two form, the sort of nomenclature that we've decided to define them is that the two form is magnetic and the one form is electric. It's a sort of nomenclature thing.
Can we like start with defining one of the fields as one form, another as two form, and somehow show that the one form is an electric field and the two form comes out to be a magnetic field.
So for
Uh,
okay, sure, we can
yeah.
we can try that.
Yeah, I think with this, so what you're saying is if we can connect it back to our good old electromagnetism.
Yeah.
So this can actually be seen because what is an electric field? It's what it deals with the field associated with charges. Now, charges moving in one dimension around them create a magnetic field in two dimensions. So, I mean, it's up to you after that, beyond that, the nomenclature. You can call the electric field as the magnetic field and the magnetic field as the electric field, but the math would still remain the same. I think that's the point that Abhiram was trying to make.
Yeah, exactly. Well, Charu, like as you asked, we can actually we can do that. But I think for that we would need a sort of. Do you have any property of electric field or magnetic field that is coming to in mind? Because we can define it and then we have to check it with that sort of property.
Yeah.
Right.
So if you have some property like some sort of theorem or something, which I don't really remember the theorems of magnetic field or
Maybe
electric field.
we'll see it in the comments. But yeah.
Yeah, maybe. Yeah. So that could be a sort of good test, I think. Just to see, because this is actually a question that whenever we study the field definitions for electric field, why is it a two form? Why is it a one form? It's a very natural question that comes up. Yeah.
And also,
so it would be a good thing to.
Yeah, definitely a good thing. And I was also thinking, so this one and two form thing, it only comes into play because we are considering three dimensions as your total space. So I'm guessing you can find this difference in any odd dimensional space, right? If we just assume that we are doing electromagnetism in higher dimensions. But what if we have an even dimensional space? Would electromagnetism still look the same?
Even exist.
Yeah, or even exist. Yeah. That's something that we can think about. Yeah,
that's something we can nicely talk about here.
So I guess the next time go for it. Yeah.
I was just going to discuss about the even dimensional thing.
Yeah, go for it. Yeah. Maybe we can end on that note and continue our next session with you explaining how this fits into the Lagrangian picture as well. But yeah, that'll give us enough time to think about these two questions that we just came across towards the end. Yeah.
So so the question basically is, will it exist in even dimension? As we see it here.
Yeah.
Okay. Well, one way I would like to start off with this question is to see. We'll start off by back. I mean, sort of what property of the electromagnetism is invariant of the dimensions that we choose. I would like to start off there.
Right.
And there I can derive how it would make sense. Does that make sense?
That does make sense. Yeah.
I mean, please stop me if it doesn't make sense.
No. That makes complete sense. I guess that will be food for thought for the next time we meet. We can have a brief discussion on this, and maybe, who knows, this can be an entire episode on its own. Yeah. All right then. So yeah, thank you so much, Aviram. And we'll meet soon. And yeah, I'll see you all.